In this video, we're going to do a review of thermodynamics and some very basic concepts of statistical mechanics that you'll need for really almost all parts of this macromolecules course. So this video is broken into three files, A, B, C. They need to be looked at in order. Okay, so in the first part, we're going to take a very brief look at the Boltzmann distribution and then look at basic concepts of work and heat, and then we'll go into a review of thermodynamics, and then finally in the last part, in part C, we'll talk about the hydrophobic effect, which is critical for understanding protein structure and stability. So we talked in the first video about this concept of the energy landscape, and the idea is that we can think about all the internal energy, all the forces that, like covalent bonds, non-covalent interactions, and so forth, that define the structure of a macromolecule. But because the molecule is not at absolute zero, all the atoms have thermal motion. And that allows the molecules to sample different energy states. And we saw in the first video an example using an empirical energy function representing a molecule as balls and springs, and the idea that things are moving around, and so a given energy term, like a bond energy, is not necessarily at its absolute minimum. And that creates, in a multi-parameter space, a very rugged energy landscape, and it's often represented by this kind of a picture. Now, we talked about the idea that we think about energies of molecules we can describe either exactly by quantum mechanics or for macromolecules more empirically by balls and springs and so forth, that we think about the structure and the internal energy of macromolecules. But what we measure generally in the laboratory, and of course at the end of the course we'll talk about doing single molecule experiments, but the idea is that if you do a measurement, let's say, of an affinity constant in the lab, you're measuring the energy of a large number of molecules, an ensemble of molecules, and it's the average behavior. And it's the linkage between the energy of single molecules and the bulk properties that is the realm of statistical mechanics. What we're going to do in this review of thermodynamics is really go back and forth between the very traditional view of discussion of thermodynamics that hopefully will be a review of freshman chemistry for you, but think about it in terms of statistical mechanics and what's happening in terms of the ensembles of molecules. And you can visualize this here. For example, this is a picture of some DNA molecules, and imagine looking over all these. They have, in this group of molecules, they all have somewhat different structures, and they're fluctuating. And you can imagine binning them by different, what are called microstates, that each of these microstates is a different conformation, therefore has a somewhat different energy. Now you can also imagine looking at one molecule and taking a movie with time. And if you do that, you will see that it's also fluctuating in time, again, because of this idea of thermal energy. And these different microstates, again, because we can measure the coordinates of each atom or group, what have you, you can then define the energy of these different microstates. So the question becomes, in the lab, if you're doing a measurement of a large number of molecules, how are these large number of molecules distributed over all these possible energy states, given that there's a restraint on the total energy, because we're at some fixed temperature and pressure and so forth. And this is, it turns out that for large numbers, for a macroscopic distribution, there's one distribution that's far more probable than all the others, and that's called the Boltzmann distribution. I'm not going to derive this. This will be discussed more later in the course as well, but the basic equation is shown here. You can calculate the probability of a particular state with some particular energy. We'll call it the ith state, so it'll be energy epsilon some I. And it's given by, the probability of that state is given by e to the minus the energy of that state divided by Boltzmann's constant times the absolute temperature. And it's normalized, and that's divided by something called the partition function, which is a sum over all these possible states. And that's basically a normalization factor so that the total probability has to sum to 1 over all the different states. So if we think about possible energy levels of a molecule, and I'm writing them as discrete levels here, sort of in the quantum mechanical sense, but you can imagine in a macroscopic sense to be closer to a continuous distribution. It doesn't really matter for our purposes. But let's think about them in discrete states. Then the Boltzmann distribution for these different energy levels gives you the number of molecules that are going to be in a given state. And relative to the ground state, the epsilon sub 0 state, that is just going to be given by the difference between the energy of the two states divided by kT for particles, okay, for single molecules. Or if you're doing a bulk measurement for, let's say in molar units, it will be RT, the gas constant, times the absolute temperature. And here are the numbers. Now, you can see from the temperature, so this distribution depends on both the temperature, here it is in the denominator here in the exponential, and the energy spacing, the difference in these energies. So let's look at the limits first. If we're at infinite temperature, then every state is equally populated because this goes to 0 and there's no difference. Or if we go to absolute 0, only the lowest energy of the ground state is populated. Okay. Now, a very important concept that you'll hear over and over again is what are called thermal fluctuations. So at room temperature, this is a very important number to know. At room temperature, let's say at 298 Kelvin, the RT term is about it's 0.6 kcals per mole, or 2.5 kilojoules per mole. Or when we talk about, there may be some discussion at the end about forces, that it's about 4 piconewton nanometers. These are all just the value of what's called RT, the thermal energy that's available at room temperature. In other words, at that temperature, that's kind of the thermal energy that allows for that gives a given distribution of molecules. Okay, so let's look at this a little more carefully. We'll consider distribution of molecules at room temperature. Now I've switched to the macroscopic form, okay, of bulk. So we have RT, and we're going to represent the internal energy of a collection of molecules with a capital E here. Okay, so we can measure, let's say, bond energies. Okay, you saw this in freshman chemistry. So the carbon-hydrogen bond, this can be measured from calorimetry, for example. It's about 100 kcals per mole. A carbon-carbon double bond is about, you can see it, it's a little more, and so forth. So let's look at something that's about 100 kcals per mole. Okay, so the difference between the bonded energy and the dissociated energy, carbon plus hydrogen with a separate, is about 100 kcals per mole. Okay, so let's pop that into our little formula here. So we can ask the dissociated energy, which will be this energy state, versus the ground state. The population is going to be e to the minus 100 kcal per mole divided by 0.6, that's RT at room temperature. So that's 4 times 10 to the minus 73. So obviously it's very small, and essentially all the molecules in that ensemble are going to be in their ground electronic state. At room temperature, you don't have dissociation of the carbon-hydrogen bond. Okay, so that's a nice illustrative example. Nice to know things are in their ground state. The bonds aren't dissociating willy-nilly, but that's really not particularly interesting. But now let's think about other kinds of states. So bond vibrations, for example. The difference between the ground state and the first excited state, vibrational state, it's going to be depending, again, on the bond and so forth, about 4 to 10 kcals per mole. And rotations, for example, we talked about rotations about single bonds in rotamers, for example, in proteins. And that's much, much smaller. Those energy level differences, those energy spacing differences are maybe in the tenths of kcal per mole. So let's look at a delta E for vibration, say, of 4 to 10 kcal per mole. So if we now do the calculation of how many molecules, what fraction of molecules would be in the first excited vibrational state versus the ground state, it's about 1 in 1,000. Now that's not a big number, but it's also not trivial. So the first few excited states will be slightly populated. Now, macromolecules turn out to have softer vibrational modes, like motion of whole domains, it turns out, with much smaller energy spacings, that correspond to low-frequency motions. And those actually tend to be better populated. So you can have sort of vibrational movements of whole domains relative to one another. In macromolecules, it's actually fairly common. Now, think about rotations. Very small spacing. So let's say we have a 0.1 kcal per mole difference in energy level, okay? Then about 85% of them will actually be in that excited state. So many of these states will be populated, and you can imagine that, for example, various rotamers can be sampled at room temperature based on this kind of idea. And that sampling of these different conformations and these different energy levels are called thermal fluctuation. So at room temperature, set by, and then the sampling set by RT or KT at room temperature allows for the so-called thermal fluctuation. So when we're not at absolute zero, you can sample different energy levels, and how frequently they're sampled is determined simply by how much, what the difference in their energy levels is. When we then look at a bulk property, what we have is the macroscopic properties result from the averaging over ensembles of molecules in which various energy levels are occupied. Very important point. So we're always looking at ensembles and looking at averages. Now, what are the timescales of these different levels? We have, for example, vibrations. They happen in the femtosecond range. They're very, very fast. On the other hand, we have things like motion of varied groups, rotation about single bonds, and so forth. Those tend to be more closer to the nanosecond range. Larger motions, like big allosteric motions in proteins, can be in the tens of microseconds to second ranges, and so forth. And this is just a little reference sheet if when we think about the timescales of these processes. Okay, so what we want to do, though, is really, most of the measurements we do in the lab are thermodynamic measurements. We're measuring energies of large number of molecules, and thermodynamics treats the energies of these processes without any reference to molecular properties. It's both the strength and the weakness of thermodynamics, because you don't have to worry about the individual detailed energies of molecules. On the other hand, it's a very abstract kind of concept, and it's very hard to learn, as many of you have experienced. Okay, now, but the way we do this is we divide the universe in an arbitrary way into the system that we're studying and the surroundings. So it's a kind of arbitrary construct, but we'll see that practically the system will be, let's say, what's in our test tube, and then the surroundings will be everything else. So we can think about the interactions between the system and the surroundings, and we can have energy transferring between the system and surroundings. For example, you start a chemical reaction, heat might be absorbed or released, or you can start a reaction and we'll do work on the system. For example, in an engine, you can have work due to the pressure volume expansion pushing on a cylinder. So you can have heat and work passing between the system and the surroundings, and those are often called open or closed. That can happen in what's called an open or closed system. You can also have matter passing between system and surroundings, and that would be for what's called an open system. An open system allows matter to pass. In a closed system, only energy can pass, and generally we'll be focusing more on the closed systems here. And what our job is really, and this is really a fundamental point, is that the energy change is always what we're measuring. We're always comparing initial and final states, and this is absolutely critical to think about when you think about something like protein folding or protein-protein interaction, a ligand interaction. You talk about the energy of that interaction, but it's always the difference in energy between, let's say, the protein not bound to the ligand, the protein itself has interaction with solvent, the ligand has interaction with solvent, they come together and there's an interaction, and we're looking at the difference in those energies. And that's a point that we'll be emphasizing over and over again. Okay, so the question then is, how does energy change? When we measure these energies and we do, let's say, a chemical reaction, what's happening? Well, there are two forms, work and heat. So work, you can define as energy that's organized on a macroscopic scale. So you can do mechanical work, for example, remember from freshman physics, mechanical work is just the force over some distance. So remember, you can raise a mass to some height, you have to apply a force to do that. That's going to counteract gravity, so it's mass times the gravitational over some distance. So that's going to change the potential energy of the mass from its value at the surface of the Earth to a new value. Okay, and work can also change the kinetic energy. You can impart movement to a particle or an object. So again, work is energy that's organized on a macroscopic scale to do something. And some examples, you can have a change of volume. Again, the example of pressure volume work pushing on a cylinder in an engine. You can change surface area, so there's a surface tension and then times the change in area is work. You can change length, so you have tension operating over some length and all these happen in cells. There are these kinds of changes happen. Electrical work, let's say through a membrane, you have a potential difference across a membrane, and then you move some amount of electricity, amount of charge through it. Okay, all these are forms of work that you can define as energy organized on a macroscopic scale. The other form of energy is heat, and you can think of that as disorganized energy that can change the temperature of an object. Now, temperature itself is related to the translational kinetic energy of molecules. So you have, let's say in a simple gas, you have molecules moving around. Their collisions lead to a transfer of energy, but it's random, it's not doing anything, so it's kind of disorganized. And you'll remember the equation that relates kinetic energy, 1/2 m times the velocity of the particle squared equals 3/2 kT. Okay, so the temperature is related to the velocity, the average velocity of the molecules in this case. Okay, now let's imagine adding heat to a system. We take a solution of a protein, we're adding heat to it. Some of that heat, that energy, is going to go into moving the protein molecules, or in a simple solution, gas, moving things around. But some of it is going to go into potential energy because you're going to start stretching the bonds, the bond angles, doing rotational movements and so forth. And other forms of kinetic energy, you can have rotational kinetic energy. You can have this translational kinetic energy, which we discussed. That's what gives rise to collisions and heat. You can also, though, impart vibrational movement or rotational movement, those various kinds of kinetic energies, and also potential energy. So only the heat, the energy that goes into changing the translational kinetic energy and the collisions leads to heat. the rest of it gets absorbed into these other kinetic energy modes and potential energy modes. And that gives this concept of heat capacity, which is the amount of heat. Formally, it's defined as the amount of heat required to raise 1 mole of a substance 1 degree, 1 degree Kelvin. And it's just given by the change in heat by the temperature at a given pressure in the case of CP, which is what one worries about in biochemistry. So again, the heat capacity reflects the ability to store energy in different modes for a given rise in temperature, okay? And that concept will come back later when we talk about the hydrophobic effect. So again, when you add heat, when you add energy to a system, or heat, you have, there are two forms of energy. Again, work is organized energy on a macroscopic scale, and the heat you can think of as disorganized energy, which are really motions on a molecular scale that are that are not organized in any way. Okay. Now let's jump back to the Boltzmann, the statistical view of work and heat, and think about this. So we talked about the idea that the energy level, the distribution of energies of particles in their different microstates amongst fixed energy levels is going to vary with temperature. So when we add heat and change, and to the extent that the temperature of the system changes, the distribution of particles in these different energy states changes. Okay? So heat is causing a redistribution of molecules amongst these fixed energy levels. What work does is actually changes the energy levels. And you can think about that in a very simple example. If you remember your elementary quantum mechanics, the particle in the box, that the energy of a given state is related to the length of the box. So let's say we take a cylinder full of gas and we expand the gas, we change the length of the box, and we're going to change the energy levels. Okay, so we'll get some picture that looks like this. So again, work acting on a system is going to actually change the relative energy levels. So that's sort of the statistical interpretation of heat versus work. Okay. So that brings us then coming back now to the macroscopic world, what we actually measure in the lab. So if we have some process, we do a chemical reaction, there'll be an internal energy change between the final and initial states, delta E. And that brings us to the first law of thermodynamics, which is simply conservation of energy. The heat change is going to be, the energy change is going to be the heat plus the work. That's the total energy. Formally, it's defined, Q is heat, and it's positive if we add heat to the system. It's negative if heat is released. Work, again, if work is done on the system, it's positive. If the system does work on the surroundings, it's negative. So again, if we transfer heat to a gas-filled cylinder with a piston, the gas expands to do pressure volume work on the surroundings, and so that would be negative work in that case, negative energy. So the first law of thermodynamics simply says energy is conserved. The energy of the universe is constant. So delta E of the universe, the system plus surroundings, is 0. So delta E has to be, it's independent of path. This is called the state function. And what it really says is that the division of work and heat needed to make some change in the energy can vary, but the change in energy, the delta E, is the same no matter how you got there. Okay. Now, the last concept for thinking about internal energy is the fact that most of what we do in biology and biochemistry happens under constant pressure. For us, it's atmospheric pressure, obviously. And it turns out it's convenient to define a new parameter called enthalpy, which is called H, and that's the internal energy we've been discussing plus pressure times volume. And the idea is that delta H equals the heat released or absorbed in a process at constant pressure. Now, for things we care about in solution, for example, typically in biochemistry, H and E are essentially the same thing. They're roughly equivalent. So we're always going to talk about enthalpy because formally that's what we work with in biochemistry. But it's basically, you can think of it as this internal energy term. And so in a process, if delta H is greater than 0, that meant that you had to add heat to the system to achieve the change in the system, endothermic. On the other hand, if the reaction you did was exothermic, then heat is released, and that turns out to be that's a favorable direction. Okay, so that ends this first video.